This video is in response to a student question about one of the assignments from Mastering Physics. So I'm going to share my screen right now so we can take a look at that. And it was 12, so I'm going to just select this. And right, okay, so this is an electric field question. We're asked to calculate the electric field strength due to these two charges at points A and B. So in a general overview, we notice that the distance from the right charge to A is the same as the distance from the left charge to A, but that won't be the case with B. So there is some symmetry that happens here. And I would expect what would happen is that the X components of the electric field are going to cancel out for A, and then we'll only have a vertical component left. Now, A has a number here. It's given as 5.1. And then the charge is given as 6.5 microcoulombs. Okay, so we can make use of that. I'm going to go ahead and do a diagram. And I'll essentially replicate what this diagram looks like. Okay, good. So we have two charges. Oops. Zoom out here for a second just to get oriented. And my paper has, some resemblance of a grid on it. So I'm going to make use of the grid. All right. So here's one of the charges right here. Plus Q. And then I'm going to go distance over F. So here's where my other charge is going to be. And then I know that the distance from here to here, from these 2 points, is 2A. And from here, this will be location A, and it's a distance A away from the axis that joins the two charges. And then in the middle, we're going to have B right here. Now let's take a look at the distances in between the two. So here's the distance from plus Q out to point A. And so this distance is important. This is going to be equal to Pythagorean theorem says A squared plus 2A squared. 2A squared is the same as 4A squared plus another A squared, that's 5A squared. So this is the square root of 5 times A. And the same thing would be true for this case. Now for B, this distance is A. This distance is A. And this distance is A. And so for that distance, we're going to have the square root of A squared plus A squared. So this is root 2 times A. And then this long distance, I'm just going to kind of abbreviate that a little bit so it's easier to see. So this is 3A. So 3A squared is going to be 9A squared plus another A squared. So this is going to be root 10A. Okay, good. And now we're ready to get go. So this is the electric field for a point charge. So this is E equals K Q over R squared. And now we know what the R's are. And then the other thing is that we need to do X and Y components. So let's do this. Let's do point A first. And I'm going to zoom in a little bit so you can see better. Now, I really like to keep things organized. So when we're doing our problem session, we're going to have a lot of stuff floating around here. So let's just try and keep all our logistics as composed as possible. So I'm going to make one column for X components and one column for Y components. And then we're going to have, so we'll make a chart. It's our chart. Wait, it's big enough. Because we're going to have the right charge. And then the charge on the left. Then we're going to add them together, and then the sum of those two is going to be X and Y components of the result. Okay, now we have to be careful of the fact that, when we do components, let's just do a magnified view about what we're talking about for A. So here's point A. And we're going to have an electric field vector from the charge that's on the right, pointing in that direction roughly. And then electric field pointing from the left. And I didn't do really a good job with that, but so this would be the A components, the X components along A. And those are likely going to cancel out. And then I also have the vertical components. So the opposite component is going to be found by taking the magnitude of this vector and multiplying by the sine of the angle. But the sine of the angle is equal to the opposite side over the adjacent. And I could do this by running through the point charge pieces, but I can also just do it by looking at the relative dimensions. So we can see that we have 2A here and then A in this direction. So sine of the area is going to be A over the hypotenuse. So A over root 5A. And then the adjacent component is going to be equal to 2A over root 5A. And of course, these are just numbers. All right, well, let's get to it. So coming to the right, this is going to be over here. Kind of running out of space here, but I think it'll work. So we're going to have minus, this electric fields point away from positive charges. So this is going to be in the negative direction. And we're going to have this root 2a, oh, sorry, 2 over root 5a, or just 2 over root 5. Times kq over r squared. So the distance is the square root of 5. The distance squared is going to be 5a squared. And then for the y component, that's going to be a over root 5 times a. So that's 1 over square root of 5, and that's positive. And then the magnitude, which is kq over 5a squared. Now for the left components, the components, at least from the electric field that's coming from the left charge, is going to be, well, it's symmetric, right? So that means this is going to be positive 2 over root 5 kq over 5a squared. So they cancel, so that's 0. And then this is also positive, so positive 1 over root 5 k q over 5a squared. Okay, so then this is 2 over root 5 times k q over 5a squared. Yeah, and that's actually our answer for this first one. Okay, well, it took a little bit of work, but we got there. So B is the one where it's going to get a little messy. If you didn't, you're wondering, geez, messy, this looks kind of messy. But anyway, here we go. So there's lack of symmetry here. So let's go ahead and label point B. And we'll do X and Y components, same thing. Going to provide a little more space for this one. X components, Y components. We're going to make a table. And we're going to have our electric fields coming from the right Q. And then the one coming from the left Q. Okay, so establish our table. We're going to look at what the sum is. And then once we get the sum, we'll do Pythagorean theorem to find magnitude and inverse tangent to find the direction of the resulting electric field. So the magnitude of our force coming from over here is going to be equal to kq over r squared. And we said that r squared is equal to 10a squared. So this is going to be kq over 10a squared. And we'll have a minus sign. And then we need a modifier based on what the cosine of the angle is going to be. So the cosine of the angle is going to be adjacent over hypotenuse. And so the adjacent side is going to be 3a. Then the hypotenuse is root 10a. And these cancel, of course. And then for the y component, that's going to be opposite over whatever we said here. So that's going to be a over root 10a. And these cancel. And then k q over 10a squared. Oof, all right. And now from coming in from the left side, cosine is adjacent over hypotenuse. So adjacent side is a over square root of 2a, and that's going to be positive. So plus a rad 2a and then the magnetic field strength is going to be kq over root 2a squared, so 2a squared. Okay, this like symmetry here, so that's going to cancel out. And then a over the hypotenuse, so it's actually the same thing. So this is going to be a over root 2a times kq over 2a squared. All right, so we're getting pretty close here. Notice that the a's cancel for all these. So this is going to be 1 over root 2 minus 3 over root 10 k q times 1 over 10a squared plus, no, that doesn't work. Sorry, we're going to have to do that from the beginning. But yeah, the same thing here. So it's just messy. I might as well put numbers in here. But actually, in this video has been long enough, so I'm just going to hold off on that. And you can decide what you want to do because, like we said in the problem, A and Q both have numbers. So you could actually stick numbers in here. But anyway, I hope this helps. This is kind of messy. I would take it all the way to the end, but it's just going to add length to the video. And I don't think it's going to add too much. All right, so I'm going to stop this right here.